Welcome back to MLT 130. In today's lecture, we're going to be covering some different laboratory calculations. Here are the objectives for today's lecture. You can pause the video and read through these on your own. The first concept we need to understand is significant figures. It is important to be honest when reporting a measurement so that it does not appear to be more accurate than the equipment being used to make the measurement allows. We can achieve this by controlling the number of digits, or significant figures. Significant figures are used to define uncertainty or imprecision in a measurement. A significant figure contains all certain digits and one uncertain. A measurement will have one uncertain digit, which is the rightmost digit. The number of significant figures in a measurement, such as 2.531, is equal to the number of digits that are known with some degree of confidence. The 2, 5, and 3, and plus the last digit 1, which is an estimate or approximation. As we improve sensitivity of the equipment used to make the measurement, the number of significant figures increases. So now let's look at some rules to determine the number of significant figures. All non-zero numbers are significant. If no decimal is present in the measurement, count from the leftmost digit until the last non-zero digit. So let's look at some examples. 1,556. All those digits, the 1, the 5, the second 5, and the 6, are all non-zero numbers, so all 4 digits are significant figures. So 1,556 has 4 significant figures. The second example, 109 or 109 has 3 significant figures, but you say, oh, it's got a 0 in it. Because that 0 is between two non-zero numbers, the 0 is actually significant. So 109 has 3 significant figures. The third example, 190, we're going to look from left to right. We have 1 that's significant, the 9 that's significant, but the 0 in this case is non-significant because it's not in between 2 significant figures. So we only have 2 significant figures in this case, the 1 and the 9. The 0 is not significant. The fourth example, we have 12,396. All these digits are significant, so we have a total of 5 significant figures. The last example is 10. We're looking from left to right. The 1 is significant, but that 0 is insignificant, so we only have 1 significant figure. Now what do we do if a decimal is present with significant figures? If a decimal is present in a measurement, start counting from the rightmost digit until the last non-zero number. So now let's look at some examples. If you have a 12.50, you have 4 significant figures. We're counting from the right, so this 0 would be significant, the 5 would be significant, the 2 would be significant, and the 1 would be significant. Now let's look at the second example, 1.004. Those zeros are in between a significant figure, the 1 and the 4, so they would also be significant. So again, you would have 4 significant figures, the 4, the 0, the 0, and the 1 would all be significant. The next example, 0.00025. You would only have 2 significant figures. If you start counting from the right, the 5 would be significant, the 2 would be significant, all the rest of these zeros would be insignificant. Okay, let's look at the next example, 0.01060. There would be 4 significant figures. Again, working our way from the right, the 0 would be significant, the 6 would be significant. This 0 would be significant because it's in between 2 significants, 2 non-zero numbers. The 1 would be significant, but these 2 zeros would be non-significant. So you have a total of 4 significant figures in that example. So let's do some more practice. So 8,600, how many do you think it would have? You can pause the video if you want to and try to figure these out on your own before you go on and get the correct answer. This one you would work left to right. The 8 would be significant, the 6 would be significant, but these 2 zeros would be insignificant. So you would have a total of 2 significant figures. The 92, both the 9 and the 2, because they are non-zero numbers, would be 2 significant figures. 1.0023. Again, since you have a decimal, you're going to work left to right. Right to left. 3, 2, 0, 0. The zeros are in between non-zero numbers. They're going to be significant. Plus that 1's going to be significant. You're going to have 5 significant figures. The next number is also a decimal, so you're going to have to work right to left. So you're going to do 1 is a non-zero number, 1's a non-zero number, but all the rest of these zeros are going to be insignificant. So you're only going to have 2 significant figures. The last example is pretty similar to the one we just did. This 0 is going to be significant because you have this 1 right here in front of it, but all these other zeros are going to be insignificant. So you're going to have 2 significant figures. Let's look at some examples of rounding with significant figures. This example asks us to round the following numbers to 4 significant figures. The first example is 1.24561, and we need to get that down to 4 significant figures. If you notice, this number doesn't have any zeros in it, so we can take the first 4 digits or non-zero numbers. So the 1, the 2, the 4, and the 5 are significant. But notice this 6 is behind that 5, so we're going to round up for that 5. So our answer is 1.246. Okay, the second number, or the second example, is 2.17 or 8734. And again, we're trying to get it down to 4 significant figures. We don't have any zeros in this particular number, so again, we can take the first 4 numbers. The 2 is significant, the 1 significant, the 8 significant, and the 7 is significant. And that 3 is not going to cause that 7 to round up, so we're going to end up with 2.187 as our 4 significant figures. The next example is 8.9328. And again, we don't have any zeros in that particular number, so we can take the first 4 numbers, the 8, the 9, the 3, and the 2, but that 8's going to cause that 2 to round up to a 3. So our answer is 8.933, and this is nanometers. Okay, this last example is 0.0344618 meters. So what did we learn about the zeros that are in front of the decimal? They're non-significant. Also, this 0 is going to be non-significant. So this 0 and this 0 are non-significant. So our first significant number is actually this 3. Okay, so that's 1 significant, 2 significant, 3 significant, 4 significant. Okay, these 2 are just going to be placeholders. Okay, so when we write our answer out for 4 significant figures, we're going to have to include those 2 placeholders, even though they're not significant. And we're going to include the 3, the 4, and the 6. Those are our 4 significant figures, and these 2 are just placeholders. Oops, I didn't mean to erase that. These 2 are just placeholders. So that's our answer, and that's meters. 0.03446 meters. Now let's discuss some general rules for rounding off. We're going to discuss 3 different rules, and the first 2 you're probably familiar with already. If the digit being dropped is less than 5, then there's no change in the preceding digit. And the example would be 12.64. Because of that 4 being less than 5, it rounds to 12.6. The second rule is the digit dropped is greater than 5, the preceding digit increases by 1. So the example would be 12.66 becomes 12.7 because that 6 is greater than 5. It rounds up. This 6 rounds up to 7. Now this third rule is the one that usually confuses people and most people's not familiar with, that we use in the laboratory sometimes. If the digit drop is 5, then add 1 if the preceding digit is odd. Add 0 if the preceding digit is even. So let's look at some examples of each one of these. So the example is 3.15. Again, the digit that we're dropping is 5 in both scenarios, but in front of the 5 is an odd number. Because the number in front of the 5 is odd, it's going to become 3.2. Okay, the next example is 3.25. Again, we're dropping the 5, but the 2 in front of the 5 is even, so it stays 3.2. We're not going to round it up to 3.3 because it's even. We're going to leave it. And that's one of the tricks to help us remember this is even, leave, odd, round up. So this would be even leave, this is odd, round up. And this helps to account for making the average really too high if you keep rounding up. If we always keep rounding up, if we do this in lab, if we do number 1 and we always round up, we're going to skew our values to the high side. So that's why this third rule is put into play sometimes. Here is our prefixes for our metric conversions, and we have a trick to help us remember these. The saying is kangaroos hop down bumpy driveways crushing marshmallows. Each letter for this little saying starts with the first letter of our prefix. So the kangaroos corresponds with kilo, the hopping corresponds with hecto, and so on and so on. But something to remember, all these prefixes can go in front of our base units, our grams, meters, and liters. For performing metric conversions, there's multiple ways to perform metric conversions, but in class and in laboratory calculations, I teach moving the decimal, the appropriate spaces to the left or right using the number line. Let's do an example. Let's do 1 liter to milliliters. Well, the first thing you want to do is draw your line out, and you can use your kangaroos hopping down bumpy driveways crushing marshmallows, and you can also add on milli, nano, and pico if you want to for your number line. Draw your number line out, and each one's going to get a little tick mark. And there's 2 more going to go in between milli, nano, and pico if you add those on. So we're going to start out with liters. That's one of our base units. And we're going to go to milliliters. That's right here. So it's going to hop 3 spaces. So we know we're going to have to move to the right 3 spaces. So if we have 1 liter, we know that the decimal is right there. So I'm just going to write over here the 1 over here so we know that's what we're working with. And we're going to have to move this decimal 3 spaces to the right. So we're going to end up with 1,000 milliliters. That's our answer. In the laboratory, it may be also necessary to be able to convert temperatures from Fahrenheit to Celsius and Celsius to Fahrenheit. So the Formula to convert Fahrenheit to Celsius is the Celsius equals 5 knots times Fahrenheit minus 32. The conversion of Celsius to Fahrenheit is Fahrenheit equals 9/5 times Celsius plus 32. It's important to know that in the clinical lab we use Celsius, and you must know some basic temperatures. 37 degrees Celsius is about 98.6 degrees Fahrenheit, which is body temperature. We usually keep our refrigerators between 2 and 8 degrees Celsius, and the room temperature in laboratories usually needs to be between 21 and 22 degrees Celsius. In the laboratory, you need to know the difference between the solute and a solvent. Solutions are mixtures of substances. The solute is the solid or the part being dissolved. The solvent is the liquid or the substance the solute is being dissolved in. There are 3 different ways to express concentrations as a ratio of solute to solvent. There's weight to weight, which is accurate but least practical. There's weight to volume, and the weights referring to a solid, the volumes usually referring to a liquid, and there's volume to volume. The weight to volume and the volume to volume are generally accurate under conditions commonly found in the laboratory setting. In percent solutions, the percent is parts per hundred. So percent solutions can be weight to weight, weight to volume, or volume to volume. So in a weight to volume solution, it is grams of solute per 100 milliliters of solvent. So in calculations involving solutions, this means making a specific volume of a specified solution. An example would be making 100 milliliters of a 20% NaCl solution. How we would do that is add 20 grams of NaCl to a 100 milliliter volumetric flask, then add water to the 100 milliliter line of the flask, and that would get your solution. The solvent is added to the solute until a specified volume is reached, and that's what we did in that example. This is referred to as bringing up or diluting up to a specified volume. It is often abbreviated as QS or quantity significant. Now we need to review changing concentrations. If you've had laboratory calculations already, this formula should be familiar to you. This is to change from one concentration of a solution to another. You're going to use the formula V1 times C1 equals V2 times C2. The units for the concentrations must be the same. The formula is commonly used when diluting stock solutions. We're given the example of how many milliliters of a 2% solution can be made from 20 milliliters of a 4% sugar solution. So we're going to try to figure that out using our changing concentrations formula. So what we're starting out with is the 20 milliliters and 4%. So this is our V1 and our C1. And we're trying to figure out milliliters for the second. So this is our V2 is the unknown, and our C2 is the 2%. So then we can go and plug that into the formula. So our formulas look like this. Our 20 is our V1, our 4% is our C1, our X is our V2, and our 2% is our C2. And then it's just a matter of solving the formula. You want to get the X by itself, so you're going to end up with an answer of 40 milliliters. Next, we could be working with percent solutions. This is weight per volume, and this is when a solid is diluted in a liquid, and you need to use a proportion formula. So let's look at an example of what one of these would look like. The example is how many grams of NaCl are in 200 milliliters of a 5% solution. And it gives you the answer there, but let's draw it out. This would be a cross your heart or cross multiplication problem. We know the 5% is going to have to go over 100 because it's 5% of 100. The grams is going to be our unknown, and that's how many grams are in 200 milliliters. So the 200 is going to go here. So this is a cross multiplication problem, or you could just off your heart. That's the way you learned in school. And that's basically the same thing that it's showing over here. So when you work that out, that's 200 times 5 equals 100x. We need to get x by itself, so we divide by 100 on both sides. So 200 times 5 is 1,000 over 100 equals x. So x is going to equal 10. So that's our answer. Next, we need to discuss dilutions. A simple dilution is the addition of a measured volume of the sample, usually serum, to a measured volume of diluent, and it's usually either water or saline. The dilution ratio is a numerator and a denominator. The numerator is always referring to the number of parts of the substance being diluted. The denominator refers to the total parts of the mixture. So the volume of the substance being diluted plus the diluent volume. And that's what usually confuses students. This is the total parts of the mixture is the denominator. So the ratio of concentration of the final total volume equals the dilution factor. So if you have an example of 1 to 3, you have 1 part of concentrate, the serum, and 2 parts of diluent. So the dilution factor, or the denominator, is 3. That's total parts. So it wouldn't just be 2, the parts of diluent, it's 3, the total volume, or total parts. Let's look at an example for a dilution. The glucose sample value was above accuracy range of the analyzer, so it was above 600 milligrams per deciliter. And the sample was diluted as follows. 100 microliters of serum was added to 200 microliters of water. This is a 1 to 3 dilution, so the dilution factor was 3. The diluted specimen was reanalyzed or reran for glucose, and the result was 356. So you take the dilution factor of 3, multiply it by the 356, and you get the true result for glucose of 1,068 milligrams per deciliter. So you can report out the patient's blood glucose as the 1,068. Another dilution example would be the BUN was above the analyzer's accuracy range of 36 milligrams per deciliter. The tech made a dilution as follows. 0.05 milliliters of serum was diluted to the volume of 0.05 of diluent. Thus, this was a dilution of 1 to 2, so you have a dilution factor of 2. The diluted specimen was reanalyzed and the result was 30. So you take the dilution factor, multiply by the reanalyzed result, and you get 60. So you can report out the patient's BUN result as 60. Sometimes in lab it's necessary to make a dilution of a sample that's already been diluted down. So this is a dilution from a dilution. So let's look at an example of this. A CK test was ran on a straight serum specimen and the results were out of range of linearity. A 1 to 10 dilution was made and the CK was repeated on the diluted specimen. The result was ran again and was still out of linearity range. Now the tech has used up all of the straight specimen and the specimen is a time specimen. So what can be done other than recollect? We can make a dilution of the already diluted sample. So a dilution of a dilution. So this is how we're going to solve it. We're going to make a dilution of the already diluted sample. So if the tech makes a 1 to 10 dilution of the already diluted 1 to 10 specimen, what will the new dilution be? So now we have to figure out the brand new dilution. So it's been diluted down twice. So the answer is you're going to multiply the dilution factors of the specimen being further diluted by the new dilution that's being made. So the first dilution was a 1 to 10. The second dilution was a 1 to 10. So the result, or the final dilution, is a 1 to 100 because you're taking this dilution factor from the first, the 10, and you take the dilution factor from the second dilution, which happens to also be 10. So 10 times 10 is 100 to get your final dilution. When you're trying to determine what dilution to use for a sample, always start with the lowest dilution possible. The lower the dilution factor, the more accurate the results are going to be. So for example, if you're a tech, and you can get by with making a 1 to 3 dilution versus making a 1 to 10 dilution, make the 1 to 3 dilution. Because if you make a 1 to 10 dilution, then your sample is just going to be less and less concentrated, and thus your results are going to be less accurate. Sometimes in lab we have to make serial dilutions. Serial dilutions are performed when it is necessary to dilute a substance in a series of equal dilutions. This is most commonly done when trying to determine the relative concentration of an antibody or antigen in a serum specimen. So let's look at an example for a serial dilution. A serum specimen was diluted in the following manner. 1 milliliter of undiluted serum is mixed with 1 milliliter of saline in tube 1. 1 milliliter of this tube is added to a second tube containing 1 milliliter of saline, tube 2. This same procedure is repeated twice more with tube 3 and 4. What is the tube dilution for tubes 3 and 4? So let's figure that out. The way you would need to do it is you would list your tubes out and you would multiply each tube by the dilution factor. So your dilution factor is 2. So if you look at your first tube, it would be 2 times 2, which is going to be 4. And then 4 times 2 is going to be 8. And then 8 times 2 is going to be 16. So it asks the dilution for tube 3 and 4. So that gives you your answer. 1 to 8 and 1 to 16 for tubes 3 and 4. Let's look at another example for a serial dilution. The serial dilution is made with tube 1 having a dilution of 1 to 3. What would be the dilution in tube 5? Again, let's list out our tubes and try to figure out the dilution. So again, we have to go with our dilution factor. Our dilution factor they give us by giving us the dilution of tube 1. So our dilution factor is 3. So 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. Times 3, 81 times 3 is 243. So our dilution factor in tube 5 would be 1 to 243. This concludes our lecture on laboratory calculations. I hope most of this was review for you, but if you need any extra help, please don't hesitate to reach out.